Okay, we're at the point of the book where we are learning about EPOL. Seems a bit anticlimactic. I was hoping to be more excited for this. So the beginning of the chapter, we're talking about select poll and signal-based I/O, or signal-driven I/O, I should say. And we went through kind of like that evolution from select to poll to signal-driven I/O and discussed all of their downsides. Now we're at ePoll, which is supposed to be the penultimate, I guess you would say, API. Is that the correct term? Second to the ultimate, the penultimate? Let's see. Pretty sure that's right. Penultimate. Last one. Last but one in a series, yeah. So this will be the penultimate, because the ultimate is IOU ring, which we will get into perhaps as part of this chapter. I might do some experimentation. There we go. Boom, 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 boom. We'll see if I feel motivated to do that. I heard that IOU ring is like pretty like involved. So maybe we put that off for another day. Maybe I put that on my projects list, my ever expanding list of project ideas. I have so many ideas that I want to do. So many things I want to like tackle. And the stream has kind of given me the venue to explore those ideas and implement those projects, implement those ideas, and learn all these things that I've just been pulling in my head. So I hopefully I get around to most of them. But I think it's natural for your desires and ambitions to always exceed your abilities. So I think that's what my mindset is at right now. Is I just feel, I'm finishing up this book. It was quite a difficult task to read all this stuff, and I got a lot out of it. Like next time anything comes up, I think one of the biggest things I got out of this book was just the confidence to know that I have a solid foundation in all the different APIs in Linux. That I can look at syscall traces now and don't feel intimidated by them. It's a confidence thing, really. Before I'd look at a sys trace, I'd see all these words. Some of them I understood, or some of them I thought I understood. Some of them were just completely like, what the hell is that? But ultimately, all of this stuff is understandable, given enough effort and time and dedication and discipline. You can understand all of it. These are machines that we have constructed. A human being has been involved until recently in the construction of every bit of these machines. They haven't evolved over thousands of millennia into some creature that we don't understand, that we have to reverse engineer. Ultimately, all these things are things that we built, and they are understandable. So that feeling of confidence really is important for me moving forward in my life and career and computing. That I don't feel like when I look at it S-Trace or going into an interview that I feel like, I'm kind of like an imposter. This book hasn't given me like, I don't think the job of this book is to give you a full understanding of all these APIs and kernel features. I think it's a survey, really. This book is a survey. It's a very in-depth survey, but it is a survey. I think looking back on it, though, I probably would have done better with a book that was A, more up to date, and B, was less mired in the details. Because some of these details are really like, it's very like in the weeds. So this would be, I think, moving forward for me, this would be a good reference material to break out if I ever need it. I doubt I'll ever need it as a reference material. I usually don't use reference materials. But if I am ever working in any of these areas intimately with the Linux kernel, and the man pages aren't sufficient for me to learn more, then I feel like this book is a good thing to touch back on, to just give you that kind of like in-depth understanding of these different areas. I guess the other thing comes with confidence in these APIs and syscall interface. With that confidence, the experience of writing C programs, reading man pages, my entire life, I knew that there was these different man sections, but I had never used like I never typed in man2 so many times in my life. And learning about man-a, which you could use for something like read, which has multiple man pages. When you quit, it goes on to the next one. That's really helpful. Yeah, sorry, I'm just thinking back about all the stuff that I learned in this book. Maybe it's not appropriate for me to do that right now. Maybe I should just read about ePOL. Okay, let's do that. Let's get her done. All right, the ePOL API. Like I/O multiplexing system calls and signal-driven I/O, the Linux ePOL event poll, so it stands for event poll, API is used to monitor multiple file descriptors to see if they are ready for I/O. The primary advantage of the ePOL API The primary advantages of the ePOL API are the following. The performance of ePOL scales much better than select and poll when monitoring large number of file descriptors. The ePOL API permits either level triggered or edge triggered notification. By contrast, select and poll provide only level triggered notification, and signal driven I/O provides only edge triggered notification. The performance of ePOL and signal driven I/O is similar. However, ePOL has some advantages over signal-driven I/O. We avoid the complexities of signal handling, e.g. signal queue overflow. We have greater flexibility in specifying what kind of monitoring we want to perform, e.g. checking to see if a file descriptor or a socket is ready for reading, writing, or both. The ePOL API is Linux-specific and is new in Linux 2.6. The central data structure of the ePOL API is an ePOL instance, which is referred to via an open file descriptor. The file descriptor is not used for I/O. Instead, it is a handle for the kernel data structures that serve two purposes: recording a list of file descriptors that this process has declared an interest in monitoring, the interest list, and maintaining a list of file descriptors that are ready for I/O, the ready list. So when they say list, that could mean a few different data structures. I guess we'll see what it is. The membership of the ready list is a subset of the interest list. For each file descriptor monitored by ePOL, we can specify a bit mask indicating events that we are interested in knowing about. These bit masks correspond closely to the bit masks used with POL. The ePOL API consists of 3 system calls. The ePOL create system call creates an ePOL instance and returns a file descriptor referring to the instance. The ePOL CTL system call manipulates the interest list associated with an ePOL instance. Using ePOL CTL, we can add a new file descriptor to the list, remove an existing descriptor from the list, and modify the mask that determines which events are to be monitored for a descriptor. The epoll wait system call returns items from the ready list associated with an epoll instance. Creating an epoll instance, epoll create. The epoll create system call creates a new epoll instance whose interest list is initially empty. So you can give it a size, which is like probably either a max size or a initial allocation size for the amount of file descriptors you assume that you're going to be using. Size argument specifies the number of file descriptors that we expect to monitor via the epoll instance. This argument is not an upper limit, but rather a hint to the kernel about how to initially dimension internal data structures. So it's probably doing table doubling. And this kind of gives it a little hint to say, just go ahead and allocate this many. You round it up to the nearest power 2, and then do table doubling off of that. Since Linux 268, the size argument must be greater than 0, but is otherwise ignored because changes to the implementation meant that the information it provided is no longer required. Okay. That's weird. That it has to be greater than 0. I guess it doesn't do table doubling anymore. As its function result, epoll create returns a file descriptor referring to the new epoll instance. This file descriptor is used to refer to the epoll instance in another epoll system calls. When the file descriptor is no longer required, it should be closed in the usual way using close. When all file descriptors referring to an epoll instance are closed, the instance is destroyed and its associated resources are released back to the system. Multiple file descriptors may refer to the same epoll instance as a consequence of calls to fork or descriptor duplication using dupe or similar. Starting with kernel 2627, Linux supports a new system call epoll create 1. This system call performs the same task as epoll create, but drops the obsolete size argument and adds flags argument to let me pull up the man page for this. Okay, that's great. And to epoll. Huh? Oh, I gotta say the epoll create. Okay. So replace size with flags. Adds a flags argument that can be used to modify the behavior of the system call. One flag is currently supports epoll close exec, which causes the kernel to enable the close on exec flag for the new file descriptor. This flag is useful for the same reason as the open O close exec flag described in section 431. Modifying the epoll interest list with the epoll CTL. The epoll CTL system call modifies the interest list of the epoll instance referred to by the file descriptor EPFD. So you say epoll CTL, here's my file descriptor. I'm going to give you an operation to perform on this file descriptor, and here's a struct epoll event pointer, which is probably going to be influence the bit mask of the events that I'm interested in. The FD argument identifies which of the file descriptors in the interest list is to have the settings modified. This argument can be a file descriptor for a pipe, FIFO, socket, POSIX message queue, iNotify instance, terminal device, or even another epoll descriptor. Interesting. I.e., we can build a kind of hierarchy of monitored descriptors. However, FD can't be a file descriptor for a regular file or a directory. Okay, so epoll cannot be used for regular files. It's quite ironic that it supports all these different file descriptors, but it doesn't actually support regular files, which is arguably the most basic of file descriptor. The origin of the reason why we have a file descriptor in the first place. It doesn't support it. Wonder why that is. Let's ask AI since it's not in the book here. Why does not support file don't have meaningful readiness semantics in the way socket pipes and other kernel-driven I/O objects do? EPOL is designed to wait until a file descriptor becomes ready for non-blocking I/O. This works for objects whose availability changes over time. Sockets, pipes, terminals, event FD, timer FD, signal FD. Terminals, yeah. Regular files are always ready. For a normal disk file, read does not block waiting for data to arrive. Write usually does not block waiting for space. Kernel can immediately service the operation via the page cache for scheduling disk I/O internally. From the kernel's perspective, a regular file is always readable and it's always writable because it goes into the page cache. If EPOL allowed them, EPOL in would always be true, EPOL out would always be true. You get constant wake-ups with no useful signal. That defeats the purpose of readiness notification. No event source to hook into. EPOL works by registering the kernel subsystems that can signal state transitions. Data arrived, buffer space available, peer closed, error occurred. Regular files don't have such transitions. File contents don't arrive asynchronously. Disk I/O completion is not modeled as file descriptor became readable. There's no producer-consumer readiness model. The VFS layer for regular files simply doesn't implement the poll-EPOL callbacks in a meaningful way. What about fuse files? They would be blocking, right? Historical architectural detail. The underlying mechanism is poll select support via poll file operation in the kernel. For regular files, the implementation basically reports readable arrival immediately and unconditionally. Because this would make EPOL useless and potentially spin, the kernel just rejects them. What to use instead? If you want async behavior with regular files, use IO U-ring supports true async disk IO. POSIX AI limited usefulness in Linux. Thread pool, common traditional solution. EPOL is specifically optimized for stateful, event-driven descriptors, not storage. Okay. That makes sense. The op argument specifies the operation to be performed and has one of the following values. We can say add the file descriptor FD to the interest list for EPFD. The set of events that we are interested in monitoring for FD is specified in the buffer pointed to by EV, as described below. If we attempt to add a file descriptor that is already in the interest list, EPOL-CTL fails with error E exists. Modify the event setting for the file descriptor FD using the information specified in the buffer pointed to by EV. If we attempt to modify the setting of the file descriptor that is not in the interest list for EPFD, ePolCTL fails with the error no entity. Delete. Remove the file descriptor FD from the interest list for ePFD. The EV argument is ignored for this operation. If we attempt to remove a file descriptor that is not in the interest list for ePFD, ePolCTL fails with the error no ent. Closing a file descriptor automatically removes it from all of the ePol interest lists of which it is a member. The EV argument is a pointer to a structure of type ePol event, described as follows. So you got our struct ePol event. We got a uint32 of our events. So that's a bit mask. And then we got some ePol data. Not sure what that is. It's another struct. I know it's a union. The data field of the ePol event structure is typed as follows. Type F union. So it's either a pointer that's in place, integer, such as a file descriptor, uint32 or uint64. The EV argument specifies settings for the file descriptor FD as follows. The event subfield is bitmask specifying the set of events that we are interested in monitoring for FD. We say more about bit values that can be used in this field in the next section. The data subfield is a union, one of whose members can be used to specify information that is passed back to the calling process. If FD later becomes ready. So we say, hey, I'm going to register this file descriptor. This is a bunch of events that I want you to monitor. And here's a little bit of data that you should let me know about when you give me this thing back. Once it's ready. Not sure what that is useful for. I know IOU ring has a similar concept. I don't think it's 64 bits. I think it's something bigger than that. That allows you to correlate data between events. So you put something on the IOU ring, you pull it off the completion queue, and you correlate events with that data. So maybe that's similar to what this is useful for. Not sure. Listing 63.4 shows an example of the use of ePol create and ePol CTO. So we call ePol create. We just give it some integer, doesn't matter. And then we create an EV event, ePol event. We assign a new file descriptor into its data field, data FD field, and we don't have to do that. This is not how it knows about the file descriptor. This is how it knows about the file descriptor, but this is just to pass it along. Why not? And then we say we want you to trigger on the read, which is ePol in. And then we call ePol CTL, saying add the file descriptor for these events. Yep. The max user watches limit. Because each file descriptor registers in an ePol interest list requires a small amount of non-swappable kernel memory, the kernel provides an interface that defines a limit on a total number of file descriptors that each user can register in an ePol interest list. The value of this limit can be viewed and modified via the max user watches, a Linux-specific file in the procsysfs ePol directory. Let's go ahead and cut that out. Procsysfs ePol max user watches. It's quite a big number. So that is 29 million roughly. waiting for events. Epoll wait. So epoll creates our epoll object, and then we can use epoll CTL to add elements to the interest list. And now we wait for events, calling epoll wait. The epoll wait system call returns information about ready file descriptors from the epoll instance referenced to by the file descriptor EPFD. A single epoll wait call can return information about multiple ready file descriptors. That's cool. I'm gonna do a little test here. Just find some Go files. Let's go to chapter 61. Go run send file, or we'll just make here. We'll do strace f build send file. So it's doing an epoll p wait. Let me go ahead and grep epoll. I need to pipe this thing using 2 and 1. Bam. Let's do a clear. There we go. So it does its epoll create 1. It actually does a close exec flag. Then it does some adds and some deletes for in and out, hup, and let. With some data, which is probably a pointer. It looks kind of like a pointer. This one failed with operation not permitted. And then these succeeded. And then we did P. So these are all on 9. So that's the one that returned here. And then we call epoll p wait. Do we talk about p wait here? We got epoll wait. There's p select. But that's in a different section. That's not an epoll. Okay. If I do man to epoll wait, it has p wait and p wait too. Select and p select. Application is safely wait until either a file descriptor becomes ready or until a signal is caught. So we talk about p select in the next section, so I'll just remember that epoll also has a version of p select, a p version, kind of like p select, and then p wait 2, which just has a different timeout argument. Okay. The epoll wait system call returns information about ready file descriptors from epoll instance referred to by the file descriptor EPFD. A single epoll wait call can return information about multiple ready file descriptors. We already read that. So we got our prototype here. Returns an integer, returns the number of ready file descriptors, 0 on timeout or -1 on error. Pass in our EPFD, and there's a pointer to an epoll event struct called EVList. So that's going to be an array. And then there's the max events, which is probably the length of the array. And then a timeout, which is, oh no, the max events can't be the length of the array because that would need to be a pointer. So that is something that we instruct epoll wait to say, I only want so many events. The length comes out of the return value. And then the timeout is just a timeout integer, probably seconds, milliseconds, maybe. The information about ready file description is returned in the array epoll event structures pointed to by EVList. The epoll event structure was described in previous section. The EVList array is allocated by the caller, and the number of elements it contains is specified in max events. Each item in the array EVList returns information about a single ready file descriptor. The events subfield returns a mask of the events that have occurred on this descriptor. The data subfield returns whatever value was specified in EVData when we registered interest in the file descriptor using epoll-ctl. Note that the data field provides the only mechanism for finding out the number of the file descriptor associated with this event. Oh, okay. So how would you... Yeah, because it's not giving you back the FD itself. How would you use it for anything else then? Has to be an FD, right? Why would you use it for anything else? Thus, when we make the epoll-ctl call that places the file descriptor in the interest list, we should either set evdata_fd to the file descriptor number as shown in listing 6834, or set evdata_ptr to point to a structure containing the file descriptor number. Okay, I guess you could do that. Just allocate something on the heap, and then never free it until the file descriptor is closed. Timeout argument determines the blocking behavior of epoll wait. As follows. The timeout equals -1. Block until an event occurs on one of the file descriptors in the interest list or EPFD or until a signal is caught. If timeout equals 0, performing a non-blocking check to see which events are currently available on the file descriptor and interest list for EPFD. If timeout is greater than 0, block for up to timeout milliseconds until an event occurs on one of the file descriptors in the interest list for EPFD or until a signal is caught. On success, epoll wait returns the number of items that have been placed in the array list, EVList, or 0 if no file descriptors are ready within the interval specified by timeout. On error, epoll wait returns -1 with error node set to indicate the error. In a multi-threaded program, it is possible for one thread to use epoll-ctl to add a file descriptor to an interest list of an epoll instance that is already being monitored by epoll wait in another thread. These changes to the interest list will be taken into account immediately. Oh, that's interesting. And the epoll wait call will return readiness information about the newly added file descriptors. That's pretty cool. So that means that one thread can manipulate the same epoll interest list that another thread's waiting on. Epoll events. The bit values that can be specified in EV events, when we call equal.ctl, and that are placed in the EV list events fields, returned by equal wait, are shown in the table 63.8. With the addition of an E prefix, most of these bits have names that are the same as the corresponding bits used with poll. The exceptions are epoll let and epoll one shot, which we describe in more detail below. The reason for this correspondence is that when specified as input to epoll.ctl or returned as output via epoll wait, these bits convey exactly the same meaning as the corresponding poll event bits. Bit mask values for the poll events field. So the first four can be both input to epoll.ctl, or they can be returned when you call epoll wait, which is in, priority, hup, and out. In is data other than high priority data can be read. Priority is high priority data can be read. Read hup, shut down on peer socket. And then out, normal data can be written. And then there's two that can be used as input, which is let and one shot, which Go uses let on its stuff, which is to say employ edge triggered event notification. Which means that when wait unblocks doesn't mean that there is IO to be done immediately on that file descriptor. But they probably use non-blocking IO as well. So that if they're, even if they can't do IO, they just attempt it and move on. And then we got one shot, which is disable monitoring after event creation. Or after event notification. And then output, we can get error and hup, which is error is occurred and hangup is occurred. Which is weird that they specify these as inputs, because it doesn't say that you can use it as input to epoll.ctl down here. So it must have some other meaning that I'm unaware of, that the book is unaware of. The epoll one-shot flag. By default, once a file descriptor is added to an epoll interest list, using the epoll.ctl add operation, it remains active. Subsequent calls to epoll wait will inform us whether the file descriptor is ready, until we explicitly remove it from the list using the epoll.ctl delete operation. If we want to be notified only once about a particular file descriptor, then we can specify the epoll one-shot flag in the EV events flag passed to epoll.ctl. This flag is specified then after the next epoll wait call that informs us that the corresponding file descriptor is ready. File descriptor is marked inactive in the interest list, and we won't be informed about its state by future epoll wait calls. If desired, we can subsequently re-enable monitoring of this file descriptor using the epoll.ctl mod operation. We can't use the add operation for this purpose because the inactive file descriptor is still part of the interest list. Interesting. Okay, we got our example program. We'll read through that. I'm going to go grab some water. I'm drifting off here. So I'm going to grab some water and maybe splash some water on my face, see if I can wake up. Alright, I'll be right back. Okay, let's look at the example program. Listing 63.5 demonstrates the use of the ePOL API. As command line arguments, this program expects the path names of one or more terminals or FIFOs. The program performs the following steps. Create an ePOL instance. Open each of the files named on the command line for input and add the resulting file descriptor to the interest list of the ePOL instance, specifying the set of events to be monitored as ePOL in. Execute a loop that calls ePOL wait to monitor the interest list of the ePOL instance and handles the returned events for each call. Execute a loop that calls ePOL wait to monitor the interest list of the ePOL instance and handles the returned events from each call. Note the following points about this loop. After the wait call, the program checks for an EENTER return, which may occur if the program was stopped by a signal in the middle of the ePOL wait call, and then resumed by sig continue. If this occurs, the program restarts the ePOL wait call. Yeah, it's expected. If the ePOL wait call was successful, the program uses a further loop to check each of the ready items in EV list. For each of the items in EV list, the program checks the events field for the presence of not just ePOL in, but also HUP and error. These later events can occur if the other end of the FIFO was closed or terminal hangup occurred. If ePOL in was returned, then the program reads some input from the corresponding file descriptor and displays it to standard output. Otherwise, if ePOL HUP or ePOL error occurred, the program closes the corresponding file descriptor and decrements the counter of open files. The loop terminates when all open file descriptors have been closed. The following shell session logs demonstrate the use of the program in listing 63.5. We use two terminal windows. In one window, we use the program in listing 63.5 to monitor two FIFOs for input. Each open of a FIFO for reading by this program will complete only after another process has opened the FIFO for writing, as described in section 44.7. Another window, we run instances of cat that write data to these FIFOs. So we got terminal window 1 and 2 called make FIFO P and Q. Then we say, hey, ePOL input on P and Q. We get them open P on FD. Open Q, and then we wait. Above, we suspended our monitoring program so that we can now generate input on both FIFOs and close the write ends of them. So then we generate QQQ, which goes into the Q FIFO. Then we type Control D to terminate that. And then we foreground the previously backgrounded P. And then we type in PPP. But we don't close P. Now we resume our monitoring program by bringing it into the foreground, at which point ePOL wait returns two events, ready to, and then it says, hey, PPP and QQQ, and QQQ did hang up. about to epoll wait. And it says, okay, there's only one thing ready on this one, which is a hang up. Two blank lines in the above output are the new lines that were read by the instance of cat, written to the FIFOs, and then read and echoed by a program. Okay, it makes sense. Now we can type Control D in this second terminal. So now we can type Control D in the second terminal window in order to terminate the remaining instance of our cat, which causes epoll wait to once more return, this time with a single event, which is the hup. Okay. Oops, sorry, I was on the wrong page there. My bad. Alright, so this is our source code. It's a page and a half. So we create our epoll, go into a loop, open up our paths, create events, EV objects, sign in the file descriptor, and because it's a pointer, you would think that it couldn't be reused, but I guess reusing it is fine. Then we go into our loop and we monitor for epoll wait. And we have some code here that once epoll is triggered, we go through each event and we handle it. If it's an input, we do our read. If it's a hang up or an error, we do our close. So it's pretty straightforward API so far. Nothing crazy. Like the signal-based I/O, that was insanity. Alright, a closer look at epoll semantics. We now look at some subtleties of the interaction of open files, file descriptors, and epoll. For the purposes of this discussion, it's worth reviewing figure 5.2, which shows the relationship between file descriptors and open file descriptions, system-wide file inode table. I don't have to go back and review that because I got it up here. I put it up in the brain. Basically, we can go back and look at it. Why not? But the basic idea is that you get a file descriptor table, which is local to each process and maps the process file descriptors to some type of structure that stores the flags like closed exec. I think it's the only flag. And then that also has a pointer to the description. The description primarily stores things like the seek offset and also its own bag of flags. And then that thing also has a pointer to the inode, which is like the actual inode for the file, which has a lot of information on it. Like a length of file, anything you get from stat pretty much would come from that. But yeah, page 95. Let me go back there real quick. What was it? It's 5.2. So long ago. That's 5.3. Here it is. exactly what I said. Oh, that's cool. You can also just hover over this and it'll kind of give you a preview, but it doesn't show you much. It must be a feature of the PDF viewer here. Alright, it's worth reviewing figure 5.2, which shows the relationship between file descriptors, open file descriptions, and the system-wide inode table. When we create an epoll instance using epoll create, the kernel creates a new in-memory inode, an open file description, and allocates a new file descriptor in the calling process that refers to an open file description. The interest list for an epoll instance is associated with the open file description, not with the epoll file descriptor. This has the following consequences. If we duplicate epoll file descriptor using dupe or similar, then a duplicated descriptor refers to the same epoll instance, and ready lists as the original descriptor. We may modify the interest list by specifying either file descriptor as the EPFD argument in the call to epoll.ctl. Similarly, we can retrieve items from the ready list by specifying either file descriptor as the EPFD argument in a call to epoll.wait. The preceding point also applies after a call to fork. The child inherits duplicate of the parent's epoll file descriptor, and thus duplicate descriptor refers to the same epoll data structure. Make sense? When we perform an epoll.ctl add operation, the kernel adds an item to the epoll interest list that records both the number of the monitored file descriptor and a reference to the corresponding open file description. For the purpose of epoll wait calls, the kernel monitors open file description. This means that we must refine our earlier statement that when a file descriptor is closed, it is automatically removed from any epoll interest lists of which it is a member. The refinement is this: an open file description is removed from the epoll interest list once all file descriptors that refer to it have been closed. This means that if we create duplicate descriptors referring to an open file using dupe or similar or fork, then the open file will be removed only after the original descriptor and all of the duplicates have been closed. These semantics can lead to some behavior that at first appears surprising. Suppose that we execute the code shown in listing 63.6. The epoll wait call in this code will tell us that the file descriptor fd1 is ready. In other words, evlist 0 data fd will be equal to fd1, even though fd1 has been closed. This is because there is still one open file descriptor fd2 referring to the open file description contained in the epoll interest list. A similar scenario occurs when two processes hold duplicate descriptors for the same open file description, typically as a result of a fork, and the process performing the epoll wait has closed its file descriptor, but the other process still holds the duplicate descriptor open. So we create our event, we sign in our file descriptor, we say add, and then we call wait after we've closed it, and it's going to wait. FD1 is going to come up, but then we're not going to be able to access it. through the file descriptor 1 that we assigned. Performance of ePOL versus I/O multiplexing. Table 63.9 shows the results on Linux 2625 when we monitor n contiguous file descriptors in a range 0 to n-1 using POL, select, and ePOL. The test was arranged such that during each monitoring operation, exactly one randomly selected file descriptor is ready. From this table, we see that as the number of file descriptors to be monitored grows large, POL and select perform poorly. By contrast, the performance of ePOL hardly declines as n grows large. The small decline in performance as n increases is possibly a result of reaching CPU cache limits on the test system. For the purpose of this test, FD set size was changed to 16,384 in the glibc header files to allow this test program to monitor a large number of file descriptors using select. So this is times taken by POL, select, and ePOL for 100,000 monitoring operations. So on the left we have the number of descriptors monitored. Then we have POL, select, and ePOL CPU time in seconds. So you can see as file descriptors go up, the CPU time goes insane on both select and POL. But with ePOL, it's pretty much constant. And you would see the same thing with signal-based I/O from what I understand. Okay. In section 63.2.5, we saw why select and POL perform poorly when monitoring large numbers of file descriptors. We now look at the reasons why ePOL performs better. On each call to select or POL, the kernel must check all of the file descriptors specified in the call. By contrast, when we mark a descriptor to be monitored with ePOL CTL, the kernel records this fact in a list associated with the underlying open file description. And whether an I/O operation that makes the file descriptor ready is performed, the kernel adds an item to the ready list for the ePOL descriptor. An I/O event on a single open file description may cause multiple file descriptors associated with that description to become ready. Subsequent ePOL wait calls simply fetch items from the ready list. Each time we call select or POL, we pass a data structure to the kernel that identifies all the file descriptors that are to be monitored. And on return, the kernel passes back a data structure describing the readiness of all these descriptors. By contrast, with ePOL, we use ePOL CTL to build up a data structure in kernel space that lists the set of file descriptors to be monitored. Once this data structure has been built, each layer called to ePOL wait doesn't need to pass any information about the file descriptors to the kernel, and the call returns information only about those descriptors that are ready. In addition to the above pattern for select, we must initialize the input data structure prior to each call. And for both select and POL, we must inspect the return data structure to find out which of the n file descriptors are ready. However, some testing showed that the time required for these other steps was insignificant. Compared to the time required for system calls to monitor n descriptors. Table 63.9 doesn't include the times for the inspection step. Very roughly, we can say that for large values of n, the number of file descriptors being monitored, the performance of select and POL scales linearly with n. We start to see this behavior for the n is equal to 100 and n is equal to 1,000 cases. Table 63.9. By the time we reach n is equal to 10,000, the scaling has actually become worse than linear. By contrast, ePOL scales linearly according to the number of I/O events that occur. The ePOL API is thus particularly efficient in a scenario that is common in servers that handle many simultaneous clients. Of the many file descriptors being monitored, most are idle. Only a few descriptors are ready. So now we talk about edge triggered notification. We've already talked about this a little bit previously. And it's worth noting that Go does edge triggered notification, which is this epoll et. By default, the epoll mechanism provides level triggered notification. By this we mean that epoll tells us whether an IO operation can be performed on a file descriptor without blocking. This is the same type of notification as is provided by pull and select. The epoll API also allows for edge triggered notification. That is, a call to epoll wait tells us that there has been IO activity on a file descriptor since the previous call to epoll wait, or since the descriptor was open. If there was no previous call, using epoll with edge triggered notification is semantically similar to signal driven IO, except that if multiple IO events occur, epoll consolidates them into a single notification returned via epoll wait. With signal driven IO, multiple signals may be generated. To employ edge triggered notification, we specify the epoll et flag in EV events when calling epoll CTL. Makes sense. We illustrate the difference between level triggered and edge triggered epoll notification using the following example. Suppose that we are using epoll to monitor a socket for input, and the following steps occur. Input arrives on the socket. We perform an epoll wait. This call will tell us that the socket is ready, regardless of whether we are employing level triggered or edge triggered notification. We perform a second call to epoll wait. If we are employing level triggered notification, then the second epoll wait call will inform us that the socket is ready. If we're employing edge trigger notification, then the second call to epoll wait will block because there's no new input has arrived since the previous call to epoll wait. Interesting. As we noted in section 63.1.1, edge trigger notification is usually employed in conjunction with non-blocking file descriptors. Thus, the general framework for using edge trigger notification, epoll notification, is as follows. Make all file descriptors that are to be monitored non-blocking. Build the epoll interest list using epoll CTL. Handle IO events using the following loop. Retrieve a list of empty file descriptors using epoll wait. For each file descriptor as ready, process IO until the most relevant system call, e.g. read, write, receive, send, or accept returns with an error E again, or E would block. Preventing file descriptor starvation when using edge trigger notification. Suppose that we are monitoring multiple file descriptors using edge trigger notification, and that a ready file descriptor has a large amount, perhaps an endless stream of input available. If after detecting that this file descriptor is ready, we attempt to consume all the input using non-blocking reads, then we risk starving the other file descriptors for attention, i.e. it might be a long time before we again check for the readiness and perform IO on them. One solution to this problem is for the application to maintain a list of file descriptors that have been notified as being ready and execute a loop that continuously performs the following actions. Monitor the file descriptors using equal wait and add ready descriptors to the application list. If any file descriptors are already registered as being ready in the application list, then the timeout for this monitoring step should be small or 0, so that if no new file descriptors are ready, the application can quickly proceed to the next step and service any file descriptors that are already known to be ready. Perform a limited amount of I/O on those file descriptors registered as being ready in the application list, perhaps cycling through them in round-robin fashion rather than always starting from the beginning of the list after each call to equal wait. The file descriptor can be removed from the application list when the relevant non-blocking I/O system call fails with again or would block error. Although it requires extra programming work, this approach offers other benefits. In addition to preventing file descriptor starvation, for example, we can include other steps in the above loop, such as handling timers and accepting signals with sig-wait info or similar. Starvation considerations can also apply when using signal-driven I/O, since it also prevents the edge trigger notification mechanism. By contrast, starvation considerations don't necessarily apply in applications deploying a level triggered notification scheme mechanism. This is because we can employ blocking file descriptors with level triggered notification and use a loop that continuously checks descriptors for readiness, and then perform some I/O on the ready descriptors before once more checking for ready file descriptors. I'm gonna go ahead and take a break there. I know it's been just slightly over an hour, but I need to take a nap. I'm dozing off here. So I'm gonna take a quick nap, and then I'll start back soon on waiting on signals and file descriptors, and we'll wrap up this chapter when I get back.